In this video, we will continue our quest to decode concatenated codes up to half of their designed distance. Let's recall the motivating idea from the end of the previous video. We had this first pass at an algorithm to decode concatenated codes, but it could only get up to the design distance divided by 4. However, we were still hopeful that we could get up to the design distance divided by 2 because of two extreme examples. In the first extreme example, the adversary introduced not too many errors per bad block, but in that case we won because we could tell which blocks were bad because we had to correct a lot of errors in them, and then we can just treat them as erasures, and that allows us to save a factor of 2. On the other hand, in the other extreme example, the bad guy introduced many errors per bad block. And that was still fine for us as well because there were not so many bad blocks, and that also allowed us to save a factor of 2. And so we hoped that by interpolating between these two different extreme scenarios, we could somehow save that factor of 2 in general, not just in these two examples. So that's the strategy that we're going to take in this video. To do this interpolation, we're going to use the following useful fact about Reed-Solomon codes. The useful fact is that if 2e plus s is strictly less than d out, where d out is the distance of the outer Reed-Solomon code, c out, then we can efficiently decode the Reed-Solomon code c out from e errors and s erasures. I'm going to leave the proof of this fact as a fun exercise for the viewer. As a hint, you can use an efficient decoder for a Reed-Solomon code as a black box. You don't need to open it up or anything. So there's an easy proof. Okay, but this useful fact is going to allow us to interpolate between erasures and errors, which intuitively is going to allow us to interpolate between this extreme example and this extreme example. More precisely, here's the algorithm that we're going to use. Okay, this isn't actually the algorithm that we're going to use. We're going to have to modify it a little bit, but here's the algorithm we're going to start with. So our algorithm takes as input a received word w, w1 up through wn out, which lives in sigma in to the n in, all to the n out. So that is each one of these wi's is a little vector of length n in over sigma in. And then we've stacked all these little vectors together to create our received word, just like we normally do with concatenated codes. And we're promised that our received word w lives close to a concatenated code word. That is, the Hamming distance between w and c is strictly less than d in times d out divided by 2 for some code word little c in c. Then we're going to do the following. For I from 1 to n out, that is for each one of these blocks in our received word, we're going to decode c in on that block. That is, we're going to let wi prime be the closest y in the inner code c in to the ith chunk wi. You might have noticed that I just moved some subscripts around here because there was a little bit of a typo. Sorry about that before, now it's fixed. Okay, so we're going to find these wi primes that we get by decoding the inner code from each of the wi's. And then we're going to do something a little bit strange. We're going to flip a coin, do something random. And with probability this, that is the minimum of 1 and this thing, 2 times the Hamming distance between wi and wi prime divided by the distance of the inner code d in. With that probability, we're going to set some parameter beta I to bot, or erased. Otherwise, we're going to choose beta I so that the encoding under the inner code of beta I is equal to wi prime, which was our sort of corrected chunk there. So basically what's going on here is that beta I is our best guess of what the original symbol in the ith place should be in the code word from the outer code. If it's the case that we had to fix a lot of errors, that is, if wi is really far from wi prime, then following the intuition we had from our two extreme examples, with high probability, we're going to call that an erasure. We're going to say, okay, I had to fix a bunch of errors. The bad guy probably did something here. Let's just call that an erasure and give up on it. Otherwise, we're just going to hope everything is okay, decode our inner code, and kind of trace things back. Once we've done this for every symbol, we now have this vector, beta 1, beta 2, up through beta n, where some of these are elements of sigma out, and others of them are bought or erased. Then what we're going to do is we're going to run cout's decoder. This is the one that takes the combination of erasures and errors from the useful fact that we saw on the previous slide. We're going to run that decoder on this vector, the vector of betas, and just return the result. So that's the algorithm. Again, this algorithm is just implementing the intuition we had on the previous slide, where if we had to correct a bunch of errors, the bad guy was probably up to something, so let's call it an erasure. Otherwise, we'll treat it as an error. Well, otherwise we'll hope that it's correct, but if it's not correct, then we'll treat it as an error. Okay, so hopefully the intuition makes sense, but what might not make sense is why this particular expression, and why are we looking at a randomized algorithm? To answer that, we have the following claim. The claim is that the expected number of beta i's that are equal to bot plus 2 times the expected number of beta i's that are incorrect is going to be strictly less than d out, the distance of the outer Reed-Solomon code. In particular, that means that, at least in expectation, the number of erasures plus 2 times the number of errors in the word beta 1 ... beta n that we're going to shove into cout's decoder is strictly less than d out. And that was exactly the condition that we wanted in order for that decoder to be successful. So intuitively, this claim is saying that, at least in expectation, the outer code's decoder is successful. Okay, so for a proof, actually, I'm going to pass on this one. You can check out the lecture notes if you're curious. There's a proof there. But if you were to go through that proof, it would explain why this probability is the thing that it is. Basically, we choose this probability to be precisely so that this claim is true. Okay, but even given that this claim is true, it shouldn't be clear yet why this is enough. So I kind of explained intuitively why it should kind of feel like it's enough, like in expectation the decoder is going to work, but that's not really what we want. We want a decoder that works, not just in expectation, but all the time. One strategy would be to try to repeat it a bunch of times and get some kind of result that works with high probability, and you could probably make something like that work. But instead, we're actually going to de-randomize that randomized algorithm that we just saw and end up with a deterministic algorithm that works all of the time. To see how this works, let's return to this algorithm up here. We're going to make a few modifications. So the first thing that we're going to do is we're going to reduce the amount of randomness that's in this algorithm. So where do we use randomness here? Right now we use randomness in this line. So every time we pick a beta I, we independently decide whether or not it's going to be an erasure or not, based on some probability that depends on that expression. What we're going to do instead is we're going to make these beta i's not be independent anymore. In particular, we're going to do this. So we're going to choose some theta in the interval 0, 1 uniformly at random. And then instead of flipping this coin independently down here, we're going to use that theta to make this decision. That is, if theta is less than this thing, we'll set beta I equal to bot, and otherwise we'll do the other thing. Notice that if this choose theta uniformly at random line were in here, it would be exactly the same as the previous algorithm. So all we're doing here is we're sort of moving the randomness outside the for loop. We're using the same randomness, the same source of randomness, for each one of these beta I decisions. it turns out that this claim still holds even with that modification. Okay, so now we have this modified algorithm, but what was the point of this? We've reduced the amount of randomness a little bit. Instead of choosing a bunch of independent random things inside the for loop, now we're choosing this one random thing outside the for loop, but we still need to do something randomly. The reason that we did this is that it's going to make it easier for us to de-randomize the algorithm. In particular, we're going to modify it in the following way. Instead of choosing theta uniformly at random, we're actually going to exhaust over all possible thetas. So that's going to look something like this. That is, instead of picking theta at random once, we're going to exhaust over all possible thetas and do this thing. Okay, probably you're a little confused about for all thetas in this uncountable set. Just hold on for a second, we'll come to that. Imagine that we could exhaust over all thetas in this uncountable set. So then we're looping over all of these uncountably many thetas. We're doing the same thing that we did before, and then we're going to get some result x-twiddle from the output of cout's decoder. If x-twiddle happens to be close to w, then we'll return x-twiddle and say, hooray, we found the right answer. And I claim that this is going to work. And the reason is that because of that claim we said before, that in expectation over theta, we're going to get the right answer. That means that in particular, there exists a theta so that we're going to get the right answer. Therefore, if we exhaust over all such theta, one of them is going to be the right answer. We'll find it by just checking, and then we'll return the right answer. So if it were possible to exhaust over this uncountable set, we'd be good. However, obviously that is not possible. We have to do something else instead. The thing we're going to do instead is to discretize the space of theta. In particular, I claim that in this algorithm, we actually may as well look at only n out plus 2 values of theta. Why is this? I'm going to return to that algorithm again and let you look at it, and maybe pause the video for a second and think about why this is true. So here's the algorithm. Why is it that I don't need to look at all possible theta, but instead that I only need to look at n out plus 2 values of theta? So the reason is that if you think about how different thetas behave in this algorithm, all that really matters is whether theta is greater than or equal to each of these things. That is, if two different thetas behave the same with respect to all of these tests, they're going to behave exactly the same in this algorithm. Another way to put it is to draw this picture. So here's the interval 0 to 1. And let's say that here's the point, the minimum of 1 and 2 times the Hamming distance between w1 and w1 prime divided by d in. And let's say that this point here is the same thing for w2 and w2 prime, and so on. So notice that there are n out of these dashes here, one for each block wi. Also notice that if we look at a particular interval here, that any theta that we were to pick in this interval is going to behave the same in that algorithm. Therefore, if we want to exhaust over all possible theta in this interval, it suffices to pick one representative from each subinterval here. So I'll choose maybe theta 0 here, and then I'll choose some representative theta 1 in that interval, some representative theta 2 in that interval, and so on, ending up with theta n out plus 1. Thus, if I just exhaust over all of these n out plus 2 choices of theta, that's going to give me exactly the same answer as exhausting over this entire continuous interval. So let's go back to our algorithm and make that update. Okay, so instead of exhausting over all theta here, first we're going to compute those representatives theta I. Notice that we can do that because we just need to figure out what these things are, and we can just compute that and then just pick whatever representatives we want. And then instead of exhausting over all of those thetas, we'll just loop over the ones that we computed. And then everything else is exactly the same. So this is our final algorithm. As written right now, it's called algorithm, the final one, take 4, but actually it has a name. This is called Forney's Generalized Minimum Distance Decoder. I think this is pretty cool. In particular, if you believe some of those details that we swept under the rug, this algorithm is able to decode concatenated codes up to half of their designed distance. And that was our original goal. Actually, our original goal was to do it efficiently. So let's take a look at that real quick. What is the running time of this algorithm? Okay, so to think about the running time, I've simplified the algorithm somewhat to just sort of denote the expensive parts. It's a good exercise to go and check that everything that I didn't list here is pretty fast and negligible compared to the cost of these things. So here's the expensive parts. So for each of big O of n out choices of theta, for each block there's n out of those, I have to decode the inner code C in at that block. Oh, whoops, my loops are wrong here. I have to run the Reed-Solomon decoder, although that's outside of this inner loop here. Okay, how long does each of these steps take? So this step here, decoding the inner code, so the length of the inner code is n in, which, since it's a constant rate code, is big O of k in, which is big O of log of n out. And that's because q out in this construction is 2 to the k in, and q out is basically the same as n out. So here we've chosen a Reed-Solomon code with n out equal to q out minus 1, and then our inner alphabet is just the binary alphabet, so we have q out is equal to 2 to the k in. Okay, so then the length of this inner code is n in, which is big O of log of n out. So decoding the inner code by brute force, this takes time big O of the size of the inner code times n in. That's because what is the brute force algorithm? We're just going to loop over all of the possible code words, check and see how far away they are from the received word, and return the best one. This is big O of 2 to the k in times n in, because the size of c in is just 2 to the k in. And I claim that this is polynomial in n. The reason that this is polynomial in n is that k in is log of n out, and so this is 2 to the big O of log n out, which is polynomial in n out. N out is less than n, the block length of the final concatenated code, and so all of this is polynomial in n. I'm being pretty fast and loose about the details here, because at the end of the day, all we're really looking for is polynomial in n. So this is definitely polynomial in n, and the reason that's true is that the length of this code is logarithmic in n. Therefore, we can handle exponential time algorithms. The next thing we need to do is run this Reed-Solomon code decoder. How long does that take? Again, this is an efficient algorithm. This takes time polynomial in n. Altogether, the whole running time is polynomial in n. Hooray, that's what we wanted. So, to summarize, success. Check. That is, we have achieved our new goal. We now have explicit binary codes near the Zioblov bound with efficient decoding algorithms up to half of their design distance. And we did it with concatenated codes. So the outer code is a Reed-Solomon code, and the inner code is some code on the Gilbert-Varlamov bound. And once again, we can find this code and manipulate it efficiently because the block length is going to be so short. However, as we just saw, in order to actually decode this up to d-1/2, we had to be a little bit clever. It wasn't the first algorithm that we thought of, but we got there eventually. So to summarize the state of things that we know so far for binary codes, the picture looks like this. We have the relative distance on the x-axis, the rate on the y-axis. The GPhy bound tells us that there exist codes which have this trade-off, but we don't know what they are, and we do not know how to efficiently decode them. However, the Zioblov bound says that there exist codes with trade-offs here, and what we just showed is not only do they exist, but I can tell you what they are efficiently, and also we can decode them efficiently. Pretty cool. Okay, that's it for this video. Thanks for watching.